ready for the second talk on this track, and I'm pleased to introduce Dinesh, who is going to talk about containers for the unprivileged use cases and talk about some fundamental problems we have in containers networking and some solutions to those problems. Please welcome Dinesh.
Thank you. Thank you all for joining this morning. For me, it kind of feels like late night. I landed yesterday. In case I fall asleep during the talk, one of you come and gently tap on my shoulder, so I'll hopefully wake up and keep going. But otherwise, I'm very excited, actually. I'm excited about what's happening in the industry. You know, one way I think about what's happening is there is this application decomposition and recomposition that's occurring. You know, applications used to be monolithic, and they're being now broken into microservices, and containers play an important role in that, right? And actually what is happening is these broken down microservices need to be recomposed together. You need to kind of stitch them back together for it to be a complete application, right? So, you know, that's another trend that's kind of occurring. So there's DevOps and, you know, decomposition of applications, and then this newer thing called service mesh, which basically composes these microservices back together into a full application, right? So that's the focus of my work in the recent couple of years. Thanks for Pavel, for inviting me to share some of that. I'm very excited about what's happening generally. In this talk, I'm going to focus on the first aspect of it. How do you decompose these applications into containers, and then how do you address some of the privilege issues associated with running microservices inside containers? And if you think about it, right, containers are great, I guess everybody knows, but one of the key barriers for the adoption of containers is security. So I mean, I've picked up some market research here for 51 Research and Forrester. Basically, when they did the survey, what is the main problem in adopting containers in the enterprise? It is security. Why is it such a problem, right? I mean, why should it be different to run an application as a containerized application versus natively? Why should it be different? Because ultimately, if you look, well, I mean, containers, there's no such thing as container. This is a mandatory joke for a container stock. You always kind of mention there is no such thing as a container, right? In the kernel, there is no such an abstraction. Then why is it different to run an application as a container versus as a native application? It shouldn't be. Containers are transparent, and that's what is different about containers versus virtual machines. They're supposed to be completely transparent. They're basically processes that are running directly on the host, right? So, you know, let's kind of think about, let's step back a little bit and define what this container abstraction should really be like. I mean, what would be desirable properties for the container abstraction? I mean, some of this theory actually helps us to ask the right questions, and then you know, implementation can align to that conclusions drawn by that conceptual model, right? So, what should the container behave like? I kind of came up with these terms. I mean, I call it conservation of privilege and conservation of resources. What that means is, if I'm able to do something, if I have adequate privilege to run an application natively, I should be able to run that application as a containerized application without requiring new privilege, without, for example, requiring root. So that's a desirable property for the container abstraction, right? If I have access to a certain resource already, I'm a regular user, I can already access network, right? Now, if I run inside a container, I should continue to have that access. Simple, right? I mean, we want to be able to define those baseline attributes for that abstraction. But it turns out the current design of containers actually violates both. privilege is not conserved and resources are not conserved. Once your application enters the containerized namespaces, it loses access to some of the resources that it had before, and it now suddenly requires more privilege to create that container. So why is that? The reason is mainly networking. Mainly networking. So when the application moves into the network namespace, and the network namespace is actually a device namespace. It's a device namespace of network devices. And then that network namespace initially has no devices, so it has no network, and now you have to do all this additional plumbing. I have network on the host, but now I need to patch that network on the host into the container. And for that, typically I would have a Linux bridge running, and then I would take, a veth-pair, which is basically a patch cable, a virtual patch cable. One end of it you plug into the Linux bridge, the other end goes into the network namespace, and you basically have network from the network namespace of your container to the host and then to the network, right? But all of these additional operations require privilege. So why is it like that? So if you think about how exactly container namespaces are designed, there is some brokenness. There is some brokenness in the way network works for containers. I mean, this is a typical way this is deployed. You have the container running, and then you have some kind of bridge. And then, in the case of Docker, you have this Docker with zero bridge, and that's the veth-pair. And then typically, if you have containers running across multiple hosts, you need some kind of overlay. Then in this case, flannel, it goes over the network. And then, so you have all of this complexity. You have a lot of complexity just to connect two processes that are running on hosts, which were already able to talk to each other before containers. Now, the moment you place these processes inside containers, now you have to do all these other things. This is particularly bad on the same host when you have two processes. In fact, they're sharing the same DIM, right? Topologically speaking, they're sharing the same underlying host, but you still need to do all these backflips just to connect to a process that is running right next to me. So there's something broken fundamentally about network namespaces in the kernel. The reason is this. The container abstraction, what it does, it takes the underlying physical resources, each resource, and then abstracts it to application level. The processor, the CPU on the host, basically becomes threads. And that is represented to the application via PID namespace. You can see consistent PID namespace and access to that underlying cores of the physical hardware. Storage devices kind of become file mounts through mount namespace, and DRAM virtual memory. So you kind of take the physical resources and then make them into application level equivalents. But when you look at networking, it is the same thing. What is on the host, which is network devices, actually are network devices, even in the network namespace. So there is a misalignment, conceptual misalignment in how network namespaces were designed. And because the application now has to reach below the OS, it ends up needing privilege. So how has this worked? I mean, how has this evolved in the last several years? So this is a standard application OS infrastructure stack. Network used to be underlay with just bare metal. With virtualization, this overlay is invented. And then with containers and cloud, that same overlay is being stretched to accommodate the needs of containers and cloud, and that's actually not working. And we see all these issues. So what is really needed is you need to step up closer to the application. You need an abstraction that's really closer to the application, and that's kind of what I call app switch. This is the work that I've been doing for a couple of years now. So let me introduce AppSwitch, right? And basically, there is a progression. There is a progression on the compute stack. From physical machines, we went to virtual machines to containers. So that's, for me, compute stack. If you look at the networking stack, there's physical network, Cisco, Juniper, Arista, that kind of network. And then with virtualization, you have network virtualization, what is called SDN. So AppSwitch, in my view, is basically an application equivalent for the network stack. So it's kind of like the containers for networking. Okay, so basically what AppSwitch does is it creates a socket namespace, if you will, or a port namespace. And I'll talk about the details of how exactly this happens. And by the way, the implementation is completely in user space. It doesn't require any kernel patch. I'm going to do a demo in a little bit. And it is actually one static binary. That's basically all it is. It's kind of like how Docker used to be long ago. It's implemented in Golang with some low-level stuff, but otherwise it's one static binary. I'll show you the demo in a little bit. So this is kind of how it works. By the way, at this point, any questions so far? Okay. Actually, this is somewhat of the high-level stuff, but I was hoping to talk about the details as I do the demo. So the architecture is basically two parts. There is this thing called trap generator, which basically intercepts the system calls made by the application. Transparently. It's not LD preload, it is basically a seccomp filter. And those traps, the traps that are generated, which are basically traps for the network-related system calls that the application makes, socket, listen, connect, bind, set sock opt, get sock opt, ioctl, fc until, you can have to cover all of those API points. And those traps, or those system calls, are forwarded to this trap handler which is running on the host. So, those two, the trap generator and trap handler, are connected with the Unix socket. So what happens is, when the application running inside the network namespace is making these calls, those calls are actually implemented on the host by this trap handler. So basically all of network for the application is conducted by this trap handler on behalf of the application running inside the container. By the way, container itself is not needed. It's a convenient use case to provide networking to the network namespace, but otherwise AppSwitch itself doesn't require use of containers. You can have any application running and the network for that application can be conducted by that trap handler. And basically what happens is you have multiple instances of this AppSwitch. Basically AppSwitch consists of all of these components here: trap generator, trap handler, and then trap handler will look at what the application is doing. If the application is, for example, doing a bind system call and then start listening, it means now there is a server, there is a TCP server that has come up. And it knows that there is a TCP server that has come up, and it's going to add this information to this service table. And then there is this component called service router, which lets other instances of AppSwitch running on other nodes know that there is this server that's running here. And basically there is a cluster that has formed, and AppSwitch actually internally uses this gossip channel to propagate the existence of these servers. And if there is a client on a different host that wants to connect to this server, it can do so by simply connecting to an IP address and a port. And that IP address and port can be virtual, can be anything that AppSwitch would assign based on user. So basically, when you create an application, you can arbitrarily decide what IP address you want to assign to that application while you bring it up. And then trap handler is going to populate the actual IP address where the application is bound to, and to the virtual IP address that it is mapped to. So basically you have that entry in the service table, and it gets propagated across the cluster, and any client will be able to then connect. So that's kind of the high level, right? Now, I can go into the details, but any questions so far? Okay. Okay, so I'm going to just list the different types of things you can do with that capability. So I mean, think of this as SDN, right? Basically, whatever SDN did, now you can do all of those things in a better way. By being closer to the application. So ultimately, what is networking there for? It is for the purpose of connecting applications. So there is no other intent for the underlying network infrastructure to exist except to connect applications. I mean, everything is an application ultimately, and all those applications actually access network through a well-defined system called interface. And that's what app switch layer arbitrates. So now you can do all kinds of functions. Every network function can actually be implemented at that layer. And a lot of this rigidity that exists in networking because of its lower level in the software hardware stack goes away. So what can you do now? You can actually, I mean, I talked about the service table. Basically, the service table is a kind of auto-curated service registry, meaning you will know what services are running in your infrastructure, all the services, and you don't have to reprogram your applications to register themselves with this central service registry. I mean, service discovery has been a big problem. When the applications were decomposed and containers were being used, now you have console and etcd and things like that. Basically, what they do is they act as this central registry. If there is a server that's coming up, it has to know the existence of this service registry. It goes and connects to it. It would advertise itself. It would say, I'm running on this IPN port, and here is a service that I provide, all of that. And then DNS itself has been extended to do some of these things as well. But it requires changes to the applications. I mean, your servers need to go and register themselves, which is a huge burden, obviously, engineering burden. So what AppSwitch can do is it automatically creates those entries in the service table. You will know all the services and fully up to date. You'll exactly know all the services that are running in your cluster. And it is auto-curated when the service goes down, when the application actually makes that close system call on that FD, on that socket. At that point, the service is down, and immediately the entry is removed from the table. So you have an auto-curated service registry there. And in fact, you can do really funny, interesting things. You can actually do automatic dependency discovery. So when you bring up an application, right? So you have your monolithic application, and then you've broken up into multiple microservices. Now you suddenly have all kinds of problems with respect to service discovery. It's not just service discovery; you have dependency discovery problem. So I mean, how do you bring up this application now? You need to have some kind of dependency graph. So I have all these microservices that make up my application, and I need to bring up these microservices in a specific order, because there is that implicit expectation when a service is coming up that the services that it depends on are already up. So you kind of need to now know this dependency graph, and who is supposed to program that. So there are tools. There are tools that discover the dependency graph. Nagios does that, and then in fact even dependency specification is a problem. I mean, even if you know as an application designer, I might know, well, my web layer depends on my app layer depends on DB, good, and I can specify this dependency graph. Now you need to specify in a way that is somewhat standard. So specification is not easy. And then, of course, you need to now enforce this. How do you enforce? So if my app, let's say Tomcat, relies on MySQL, I need to make sure that MySQL is fully up and listening before Tomcat can start. And what is the way I would do that? I mean, I might write a liveness probe or something like that. Basically, check that MySQL is fully up, and then Tomcat can go on. Typically, what ends up happening is people just wait for sufficient time before bringing up Tomcat. That's kind of what ends up happening. And then you're just waiting. Your application takes a lot longer to come up because now the wait for your application has to be conservatively long, and you just end up waiting for 10 minutes. not good, right? So discovery of dependencies is a problem, specifying dependencies is a problem, and then enforcing the dependency order is a problem. So all those things actually go away with apps. And I'll show you how this works. So basically, the model is you have the service table which has all of these services. Now I can create references for a service. I can create a reference. And when I create a reference for a service, I specify the labels. The reference has a label selector. And all of these services actually have some labels attached to them. And these services acquire those labels when the microservice of which this service is a part of was created. When the microservice is coming up, the user actually attaches some labels to them, and those labels are inherited by the servers, or TCP, UDP, whatever servers that are created by that microservice, inherit those labels, and they all show up in my service registry. I can create reference to any of those services that may or may not exist by specifying an IP address and a port. This is how I want to access the service that I'm about to specify, and this service reference has this label selector, and the label selector might be I'm looking for this particular application, app equals whatever, and then port equals something, whatever, right? So that's how you would specify the backend service, which should be accessible at the IPN port I specify as part of this reference. Actually, this reference, I call this vService. The name is not written in stone. We might change it, but basically, this vService has an IPN port, and then this label selector which points this IPN port to a service. Or a set of services, actually. There might be multiple services that match this label selector, in which case AppSwitch actually internally load balances across the matched backend services for this reference. So once you have that, you kind of have load balancing built in. And then you can also use these labels as a way to enforce access controls. I'll show that as well in the demo. So that's basically what this proxyless client-side load balancer is. You don't have the central load balancer just by virtue of these references. You have load balancing already available to you. And this reference also acts as an invariant. The invariant that points to the service. The service might actually move to a different node. Because it's shut down here, the node died, whatever, the service is now brought up somewhere else, but the reference actually stays the same. The service would continue to be accessible at the IP address and port specified as part of this vService reference. So you have this IP preservation, server IP preservation. And you can specify arbitrary IP addresses. Basically, if we use this, so we have this product called AppOrder. We take legacy applications like SAP, JD Edwards, Oracle, eBiz, those kinds of applications which might have static configuration in them with static IP addresses. And now I want to containerize this application. I want to automatically run this application in a container on Kubernetes, GKE, AKS, or whatever. And there is this deep dependency on specific IP addresses for these applications. And those are reconciled by this thin layer of AppSwitch, basically by providing specific IP addresses. So when I'm bringing up this application, I give it whatever IP address of my choosing, basically whatever IP address that the application was using on the source environment, that same IP address will be given to the application at the target on Kubernetes, on containers, and the application will continue to run happily. You don't have to reconfigure. Sometimes these applications are so old, you don't even know how these configuration files are formatted or where they exist. So it just makes it easy to kind of a kind of first order modernization of your applications by decoupling these dependencies on the network identifiers underneath. So you also have this client IP preservation. So when you have proxies, or there's other ways of doing this. Obviously, in the case of Kubernetes, you might have ingress controller, some kind of proxy. Istio is a proxy. So you might have some proxies that help you get around some of these issues, but they have their shortcomings. When for example, I'm a server. And somebody's connecting to me across the internet, and there's a proxy in front of me, and basically proxy is connecting to me, not the end client. So when I want to know who is connecting to me, I always end up seeing the proxy address as the source address. So I can't make decisions based on the client source. Or if I'm logging who is connecting to me, basically is going to be proxy entire time, right? So that's not helpful. So the client IP, the real client IP, has to be preserved at the server side, and that can be done with this kind of with this layer of virtualization. So you have client IP risk preservation, and if I'm moving an application to a different environment, and I would now want to access alternate services than my source environment. I might want to repoint my application to different services at the target environment. I can do that. Basically, implementation-wise, the application is making a connect call. I can swizzle the connect IP address to the alternate server that I want this application to reach at the target. So you have fine-grained app-level observability. So it's not the network packet deep inspection and things like that. I actually have meaningful interception points. I know which application is making what call. I don't have to do a lot of processing to retro-infer what the application is doing based on deep packet inspection, because I have good semantic content available in that API. Once I have this, now I can also do things like transparent TLS insertion. Basically, I can encrypt all traffic. The application itself might not support encryption, but you can retroactively induce encryption because again, all of this is being arbitrated by this layer. So that's possible, and in fact, you can. So what is the cost of doing all this? Is there overhead for this? Actually, no. In some cases, the performance can be better than native. In some cases, small cases actually. If I brought this example. So you have two processes running on the same OS, same host, and they're doing this network. What happens? You have to go through all these veth-pair, Linux bridge, and then host TCP stack, and then back all the way into the other container. So in this case, when the application asks for a TCP socket, I would transparently return a Unix socket instead. And when the application is making a TCP connect, I would say I would actually behind the covers do a Unix connect. So my application client and server are thinking they're talking over TCP, but really they're talking over Unix, and they don't know that. The application might make get sock name, get peer name, and things like that. I bluff, application is happy, and it's just running faster. So in fact, you can actually reduce the latency. By the way, so this is integrated with Istio. We've done this work. So I've seen huge improvements in latency compared to this. There's a blog on Istio that I wrote about this. So questions before demo? Yeah.
Have you tried running a browser in the?
Yeah, I have. Actually,
can you please repeat?
Yes.
The question.
Have I tried running a browser under AppSwitch? Actually, I have, but others have too. Somebody did this. Somebody actually ran Mozilla Firefox under AppSwitch and wrote a blog about it. It's on appswitch.io. So this is in several months ago he did that. So there's no limitations, right? So how is this interception working? This is not LD preload. This is not just ptrace. There are some ways of doing this. For example, eddy preload is limited to dynamically linked applications, but this we use for serious enterprise applications, Oracle EBIS, SAP, right? And veth-pair ND and BPM and those kinds of applications, and we run them under AppSwitch. So there's really, and the generality was the first requirement for this. This needed to work for very poorly behaved applications, not the greenfield 12-factor apps. What about traffic filtering? What about it? So here's the thing, right?
Traditionally, we can use some complex IP filters or access controls. As I understand, in your solution are also going through sockets.
Yep.
So how we can guarantee that some third-party process on the same host not interrupt our traffic or not sync or something like that?
So let's think about it this way. So the application is unprivileged. I mean, AppSwitch itself is unprivileged, by the way. This completely runs in not only user space, it runs as a regular user, the same user as the application. So if you can do something as yourself, you can do through AppSwitch. I mean, that's basically the premise. And if you cannot do something as your regular user, you cannot do that with AppSwitch as well, because AppSwitch doesn't have any more privilege. And in terms of the network filtering and what is happening, I mean, all these lower level network tools, the application is really running on the host. Application is really using the interfaces that are available on the host. So on the network, you will see those IP addresses and those ports. The application might think differently, because you have assigned it whatever IP address. I mean, in my example, I might give it 1111. That's my IP address, right? So the application thinks it has 1111, but it doesn't. It is really using whatever interface that you have on the host, and that's what all your network tools will observe. So it basically is a convenient glue between the application and the operator, ops, dev and ops. So basically, this kind of removes the friction. I don't have to talk to the network operator for me to acquire an IP address to run the application, or for me to program the DNS to acquire a name. So a lot of those things become non-issues. Other questions? Oh, by the way, I have a lot of interest in containers in general. I mean, actually, some of these concepts originated in my work long ago as part of my PhD work, and I've written a book about how containers, the design space of containers, and exactly what containers are built on conceptually, not just in terms of commands. I have some books here. Whoever asks questions gets a book. Okay, I think I'll do a demo now.
Hi, one more question, please.
Yep.
So, what about vulnerabilities? So, I see you use two sides. On the host,
yep,
trap sender, for example, and in the container, trap receiver, yes? Trap receiver.
Mm-hmm.
So, when you use native Linux bridge, or v-ets, and so on, you get all network traffic transparently. But when you use application on the host side, and if the application have some vulnerabilities, traffic or hackers can use such vulnerabilities to hack your host hypervisor, for example. But when you use transparently for network, they can hug only container environment, not your host. What about vulnerabilities and network security? My question is.
So again, the point of this is AppSwitch is unprivileged. So you are bound by the privileges that your user has.
For example, we have in the kernel some vulnerabilities, and we can roll up privileges in some.
How would that work? It's like any process that is running on the host as your user. So I mean, think about it this way, right? So I'm a regular application, right? And let's say I am connecting to google.com. I'm supposed to connect to google.com, but my application, by mistake or whatever, I'm connecting to ibm.com. Now, I'm a regular user. I made that mistake, and now I don't have the source code for it. Should I be allowed to change that ibm.com to google.com? I should be. I mean, you can do that today. You can do IP tables and things like that, but they all require privilege. But with this, you shouldn't need more privilege to tweak something that is completely inside your program. So AppSwitch basically runs as your user. It's like you are reprogramming your own application, and you should be allowed to do that. And that's all AppSwitch actually does. So it doesn't, see, that's what I call privilege drift. So there is no drift of privilege with AppSwitch. So you're kind of bound by what you're already allowed to do. So, right? I mean, I'm not acquiring any new privilege.
May I have one more question, please?
Yeah.
There
you go. Yeah.
Do you actually create any socket descriptors on the host on behalf of the application?
That's right. Yeah.
So do you inject them back to application or not?
Do I inject
these new descriptors back?
That's right.
Do you inject them?
Yes.
In which way? How do you inject them back?
Oh, okay. Yeah. Good. So the application is making socket system call, and it is intercepted, and the host actually creates the socket.
Yeah.
Sometimes it might create a unique socket, like I was saying, and that FD is passed back to the application over that unique socket that connects the trap generator and trap handler. And in terms of the mechanism, how exactly the transfer happens.
Is there any agent on that side? Or?
No agent. No agent.
Is it a ptrace thing?
Yeah, actually, what I do is a little embarrassing.
Okay, that's the most interesting thing.
That's actually pretty interesting. Yeah, right. So I was hoping that somebody would ask this question so I can answer this. I would map a little page in the application at an unused address range, and then there I have a little static code that receives the FD.
So you inject a small agent into the memory of the application.
Yes, transparently.
Yeah.
It runs in the context of the application itself. Yeah. And by the way, I mean there is no overhead for some of these things because I'm not in the data path. The crucial difference is I'm not in the data path. I'm only intercepting, FDs and connect and those kinds of things, but not read-write, because they do not carry IP addresses as arguments, which I would otherwise have to translate. So if I do a connect, I have IP and port in that connect call, and I would have to intercept and change the IP, IP address and ports, because I might have. I mean, the point of network namespace is this, right? I mean, what is the problem that it is ultimately solving? It is basically allowing you to run multiple applications on the same shared host, even if those applications were to use the same port. I mean, I should be able to bind to port 80, and I shouldn't get an EADDR in use. I mean, the point of containers is basically that, isolation. And it solves, AppSwitch solves that problem not by creating a different IP address per container, which I think is wrong, because applications should not be discriminated by IP addresses. Ports are what they are for. Ports basically are to differentiate applications, and that's what AppSwitch does. Basically, it assigns different ports. Of course, AppSwitch can also assign different IP addresses if the user so desires, but basically, it doesn't limit you to requiring applications and these containers applications to carry their own IP addresses and then have all these other privilege issues and things like that.
Yeah, some applications check socket credentials, for example. What's going to happen with them? Because they change. Using this approach, they change. Because the process that created sockets is different. Yep. It probably has different UID, GIT, and definitely has a different PID.
Different PID.
Yeah.
Okay.
What if an application actually uses this information?
What interfaces use PID? What
sorry?
socket interface uses PID?
For Unix namespace?
Unix sockets, peer credentials. Peer credentials, you mean?
Yeah.
Yeah. Okay. So right now, AppSwitch projects TCP sockets. I haven't implemented support for Unix, but some of those, you can virtualize. You can virtualize your way out of some of this thing. I mean, at this point, I've seen so many of these funny API points that I feel confident that almost any interface can be worked around. But I haven't implemented this.
I see. So you probably have the page listing limitations of this approach.
Yeah. I mean, like I said, we are running some heavyweight applications in this, and we haven't seen any problems so far. I mean, we have seen problems, and then we worked around it.
Okay, thank you.
Yeah, all right. I have about 20 minutes and maybe some more questions. So here's what I'm going to do. I will run. So AX is the command, and by the way, you can all try this. It's on Docker Hub. So here's what I'm going to do: Docker CP. So if I do this, actually I already pulled this image. So what I'm doing is there is a Docker container with AppSwitch on Docker Hub. I'm just pulling that container image, and in that AppSwitch binary is there, and I'm just copying it to /temp. So I mean that's the installation of AppSwitch basically on this host. That's all it needs. I needed to do, and I'm going to run it. And actually, before I do that, I need to know the IP address of this machine here. By the way, the configuration is there's 2 virtual machines on this laptop. The first one is host 0, the top 2 terminals, and host 1, bottom 2 terminals. And I'm going to run the AppSwitch binary that I just pulled. And there is daemon, and then there is client, just like Docker, I just have to give it the IP address of the IP address of the interface that I want AppSwitch to use. So I've done that. And so now this daemon is running. So basically this daemon represents the handler and the service router and all that. So that implements that functionality. So now let me run. By the way, who am I? I'm just a regular user, and I've run it. Right? And by the way, it's a standard CentOS 7, I think 7.2 or something, unmodified kernel, very old, nothing special, and no kernel modules and things like that as well. Okay, so I'm going to run, just for clarity, I'm not running those BPM and those kinds of applications, just a simple web server. I'm going to run that application as a container to show that I can plumb network into this container without privilege. And the first thing that I would do is net equals none, which means there's network namespace, but it has no devices in it. And I'm going to just make it a regular user. And I'm going to map /temp where I downloaded this AX binary. And I'm going to make that the entry point inside the container. And I think that's probably all I needed to do. I'm going to run Python alpine image. And AX daemon I already ran before. I'm going to do AX client, and the subcommand for that is run. So entry point is AX. So I'm basically doing AX run. And when I'm running whatever I'm running here, I'm going to give it an IP address, and I'm giving it 1111. You know, it's completely arbitrary. And I'm going to now start that server. So if I do this, well, it's running. It's actually listening on 1111 port 8000. And net equals none, right? So there's no network, but this application is running, right? OK. I'm going to try to connect to this. Actually, before I do that, let me create a daemon on this other host as well. And I would do it exactly the same way. I'm going to pull the app switch binary to /temp. And then I'm going to run the daemon. And actually, wait. The IP address of this host is this. So this is the IP address of this host, and I'm going to point this daemon to the other daemon, so they can form a gossip channel cluster. So there. I have the daemon running. Actually, I can just check. Oops. OK. So this has 2 nodes in this cluster. And I'm going to do pretty much the same thing, except I'm going to run a client here. Again, net equals none. A regular user, map the binary into the container, make it entry point. And by the way, this container image is very standard official image, so the container itself doesn't have anything funny in there. It's a standard container image that I've pulled off of Docker Hub, except that I'm mounting the app switch binary into it and then running it inside. OK, so there is this convenient curl Docker image that I'm going to run. Again, pretty much the same way. I will give this another IP address, 2222 in this case, and I'm going to run curl port 8000. So it works. Right? So this I'm able to curl this server that's running on this other host. What else I can do? So I will create one more server. And give it the same IP address. So I have 2 servers now running, 2 web servers, both running on IP address 1111 and port 8000. No port conflicts. Why is there no port conflict? Because in reality, it is running elsewhere, but that's not known to the application. And let me try to connect. Oh, this time it went to this. I did the same curl again. I curled 1111, but this time it load balance. It's kind of internal load balancing, right? So I'm going to do this several times. It goes to different one each time. Right now, the strategy is random. In fact, what I can do, I can just put a watch in front. What was the question? Sure. Yeah, I mean, it's a load balancing strategy. I mean, right now, yeah, we implemented a couple strategies. It's round robin, random, and there is some preference to local client, local servers. If there is a server that's on the same host, then it would always go to that. But that's not a good demo because then I can't show the load balancing. So it's running on a different host. And in that case, it actually uses the Unix socket optimization. The server is also on the same host, so it would then use Unix socket instead. Be faster.
Will it be possible to increase, for example, priorities?
So just to explain this, I'm running this under watch, and you can see that it is load balancing. I'm going to cancel this. Yeah. OK, sorry, go ahead.
Well, is it possible to prioritize one of the Dockers, and increase or decrease prioritization while you are running some load?
Sure. I mean, you can do all kinds of funny things, interesting things, right? The load balancing itself can be implemented as a plugin to this, so that's not hard coded. There is a. I haven't talked about the whole gateway concept. That it's all in documentation actually, but you can implement the load balancing strategy yourself and make it a plugin into AppSwitch. You can do based on locality, load, whatever.
Any options aside from the addresses like this?
Sure. Yeah, sure. OK, so let me show that then.
And if one of Docker dies,
Yeah.
so everything will be transmitted to only one Docker?
That's right. Yeah. I mean, that's the primary use case for load balancing, right? Yeah. Redundancy. So let me answer this question by showing a different feature. I'm basically killing those servers, and I'm going to restart this, but I'm going to give it what I call labels. I'm going to attach a label to this application, and I'm going to call this role equals prod. So now this is a prod server, right? So that's running. And I'm going to attach a different label to this. Both carry the same IP address. Let's say department equals accounting. So I have two servers running, one with one label, other with a different label. And I'm going to try to connect. It can't connect now because the client doesn't carry any of these labels, so it's not able to connect, and I'm going to get out of this. And let me give this. I'm going to call this prod client. So now it goes to production server. So it always goes to production server. It will never go to this other thing because it carries this label. And you can have arbitrary label expressions to select who you go to. So if I give another label to this, now it will load balance actually. So now this time it went here. So now it carries both labels. So it is now able to do load balancing across these two. So there's a whole set of features, but I'm going to save some time for questions. Yep.
Yeah, thank you. So the premise of the talk was containers for underprivileged. So is it possible now to run Docker containers that are networked without being in a Docker group and having basically root access?
That's the point. That's what I've shown. Yeah, exactly. There may be some caveats. I mean, so this hasn't been considered adequately. So Docker daemon and container managers in general do extravagant things because they're running as root already. They may do things as root or require root even for things that they can otherwise do without root, right? So there may be things like that. I mean, I haven't actually done deep integration into Docker daemon and make it run as a regular user, but certainly this is the core of it. Basically, the network is what is holding it back. But container managers should run as regular user. That's the premise of this talk, yeah.
Yes, but is it possible right now to use app switch to run to install somehow any container runtime and run containers without a root access right now? Is it possible?
Sure. Yeah. See, I mean, you can run init under app switch. In fact, that's what we do. In most cases, I actually don't know the entry point for the application that needs to be run. So you just run has been init under it. And basically, all your applications are now running under app switch. And your host, all applications on your host are running under app switch. So you can do these kinds of things there.
Yes, but for instance, here you ran as a Docker run command, and it requires, as I remember, it requires you to be in a Docker group to execute.
Okay. Yeah, see, the thing is, yeah, you're right. This is not integrated into Docker. Docker daemon still needs to run as regular, as root. The Docker daemon is running as root, and Docker client is accessing this var run Docker socket, which is in Docker group. So it is somewhat incidental that I'm using Docker here, but otherwise you can also do this with unshare. So I mean, the point is not to do this deep integration into Docker per se, but if you create a network namespace, you can do unshare, and then I'm using Docker just because it's convenient, but basically you can give networking to a network namespace without privilege. You will need to do some integration with Docker or LXC, and we are going to do that. Yeah, we have patches actually. We're going to send them. Yeah.
Thank you.
Yeah. Yeah.
I'm sorry if I missed, but how did you pass the socket of your server part to your client part in Docker? The socket between the server and the client.
Yep.
How did you pass it to the Docker instance?
So there is an application client and an application server. There are different sockets.
No, AppSwitch server and AppSwitch client.
Oh, AppSwitch daemon.
Yes.
Yeah, AppSwitch daemon creates the sockets on behalf of the applications that it is serving.
Yes.
And those sockets are passed into the applications address space, applications file table, by this injection. So the application is there, and then I find an open space in the VM address space, and then I map a couple pages. Is that what you're asking?
No. How did you pass the control socket of AppSwitch to the container, to the Docker container?
When you say control socket, it's mainly the socket that the AppSwitch daemon has created on behalf of the application that gets passed over the Unix socket that is connecting the AppSwitch client.
That socket that. Sorry. How did you pass the socket between the AppSwitch daemon and AppSwitch client to the Docker container?
So AppSwitch daemon has this trap handler, right? One of the things that AppSwitch daemon, one of the components of AppSwitch daemon is this trap handler, and there is a trap generator, which is injected code, which is running in the context of the application, and they're connected with this Unix socket.
So how did you pass that Unix socket? How did you pass that Unix socket to the container?
Okay, so there is a socket. There is a Unix socket FD, a Unix socket server that is created by AppSwitch daemon.
Yes.
And the client will connect to that. Who is the client? The client is the injected code that's connecting to the Unix socket server created by AppSwitch daemon.
It's
and then now you have
temp AX.
Yes.
Ah, sorry. Okay.
Yeah.
That's what I.
Okay. Okay, more questions.
The question is, am I right that both client and server should be run inside this app switch, or is it possible, for example, run several servers inside this Docker app switch or whatever, but run client at just usual application and provide it with target IP address and maybe gateway that is maybe some public IP addresses? So am I right, use app switch for servers only, but client just use the usual network?
Good. That's a really good question. I missed that. Yes. So there is an ingress support. You can expose. See, I'm giving this server 1111. Obviously, some browser in China wouldn't know about this 1111, right? So then I can expose the service via this reference that I talked about. So I'm creating a reference to this server that I've just created. And that reference can be marked as external. Then what happens is you can specify an interface on your host and an IP address that is routable and some port. So basically, you are now mapping an IP port on the host to your service. And this is routable IP address, so anybody can reach to it. And then, in fact, this can be on any node on the cluster. So the app server could be running on one node, the interface could be configured on a different node in the cluster, and AppSwitch basically does the plumbing. I just wanted to show a little video here. Can I click it? OK. Yep. So we're working basically, how can I get audio? Can I? All right. Anyway, so we're working hard. I mean, basically, see, here's what we're trying to do. We basically think that this is the right way to do networking. And a lot of this SDN is just backwards. I've written some blogs about it. Same with, it's kind of like, the AppSwitch to me is like the containers of the network stack. So basically, AppSwitch does to SDN what containers have done to VMs. So we're working with Kubernetes. This is Tim Hawken at Google. He said some things about AppSwitch I wanted to share. Also, I have audio? Maybe. OK, I'll try. Nope. All right, no worries. But these links are online, and I think these slides will be shared. So that was Jerome of Docker kind of talking about AppSwitch.
No. We're running out of time. Guys,
right.
You have discussion zone on the first floor. You can continue. And now we're going to have the lunch time.
All right.
Lunch is free. Restaurant is near the stairs on this floor. So thank you, Dinesh. Please applause.
Thank you, guys.
Yeah, and you should...